Hello everyone, welcome back to my channel. I am Sushmita of BSc second year 4th semester college roll number 205036 of Isabella Thoban College, Lucknow, and today in this video I'll be covering these topics. The topics are theory of equilibrium, second is condition of equilibrium, third is types of equilibrium, that is stable equilibrium and unstable equilibrium, and the last three topics I'll be covering out through an example. The topics are application of theory of equilibrium on strings, second is application of theory of equilibrium on system of forces, that is point source central axis, and the third is application of theory of equilibrium on virtual work. Now, what is theory of equilibrium? A body is said to be in equilibrium if it is at rest or moving with uniform velocity. In other words, if the linear and angular acceleration of a body are zero, the body is said to be in equilibrium. Or we can say that when two or more forces act on a body such that their resultant or combining effect on the body is zero and the body retains its state of rest or of uniform motion, then the body is said to be in equilibrium. Stable and unstable equilibrium. So when a body moves on a smooth curve, then it takes the different positions. It will rest at points A, B and C, which are the positions of minima and maxima of the curve. Now if the body is slightly displaced from the position of rest, that is at A or C, then it will try to come back to its original position of rest. Here the equilibrium of body is stable. Whereas if the body is displaced from the position of rest to the position at B, then it will try to go further away from the original position. Here the equilibrium of the body is said to be unstable. Stability and instability of body with its center of gravity. So through three cases I'll be explaining out. So the case 1 is if the center of gravity lies on the vertical line through the point of contact and it is below the geometric center of the sphere as shown in the figure, and the sphere is slightly displaced, then it tends to come back to its original position of rest. This is the position of stable equilibrium. The second case, if the center of gravity lies on the vertical line through the point of contact and it is above the geometric center of sphere as shown in the figure, and the sphere is slightly displaced, then it tends to go back away from its original position of rest. This is the position of unstable equilibrium. And the third case is if the center of gravity lies on the vertical line through the point of contact and coincides with the geometric center of the sphere and is slightly displaced, then it will remain in equilibrium. In this case, the equilibrium is said to be neutral. Now to determine the nature of stability. So let Z be the height of a body from the point of contact. Express Z in terms of a variable, then the position of rest is given by dz by d theta equals 0, which on solving gives theta is equals to alpha, alpha 1, alpha 2, alpha 3 and so on as the different positions of equilibrium. The first condition is the equilibrium is stable at theta equal alpha if d2z by d theta 2 is less than 0. In the second condition, the equilibrium is unstable if d2z upon d theta 2 is less than 0 at theta is equals to alpha. However, d2z upon d theta 2 and for theta equal alpha, that we consider d3z upon d theta 3 and d4z upon d theta 4. Third is for position of rest d3z upon d theta 3, the equilibrium is stable or unstable according as d4z upon d theta 4 is greater than 0 or 0 at theta equals to alpha. Here's a note. If Z represents the depth of center of gravity of the body from the fixed horizontal plane, then the equilibrium is stable if d2z upon d theta 2 is less than 0 at 0 is equals to alpha, and unstable if d2z upon d theta 2 is greater than 0 at theta is equals to alpha. Now the general conditions for stability of a body resting on another body. So when a body rests on another body, the equilibrium is stable if 1 upon h is greater than 1 upon small r plus 1 upon capital R. And second is the equilibrium is unstable if 1 upon h is less than 1 upon r plus 1 upon capital R. Here the h is the height of center of gravity of the body at some point of contact. Energy test of stability. So for a system in equilibrium under conservative forces, first the potential energy is minimum for stable equilibrium and the potential energy is maximum for unstable equilibrium. Now here's an example based on the theory of equilibrium. So the question is, a lamina in the form of an isosceles triangle whose vertical angle is alpha is placed on a sphere of radius r so that its plane is vertical and one of the equal sides is in contact with the sphere. Show that if the triangle be slightly displaced in its own plane, the equilibrium is stable if sine alpha is less than 3r by a, where a is one of the equal sides. Now the solution is, let ABC is an isosceles triangle with AC and BC as equal sides, and angle ACB is equals to alpha. So let AC is equals to BC is equals to A. If G be the center of gravity of triangle ABC, then CG is equals to 2 by 3 CD, which is equals to 2 by 3 A cos alpha by 2. If H is the height of center of gravity from the point of contact, so H will be equal to PG, which is equals to CG sin alpha by 2, which is then equals to 2 by 3 A cos alpha by 2 into sin alpha by 2, which is equal to A by 3 sin alpha. Here capital R is the radius of lower body, that is sphere, which is equals to small r, and the small r is the radius of upper body, that is plane in contact, which is equals to infinity. For the stable equilibrium, we have 1 upon h is greater than 1 upon small r plus 1 upon capital R. So this is equal to 3 by a sin alpha, which is greater than 1 upon infinity plus 1 upon small r. This implies 3r is greater than a sin alpha, which implies that sin alpha is less than 3r by a. Now the application of theory of equilibrium on strings. So this topic I'll be covering out through an example. So the question is, a string of length 2L is freely hanging over two horizontal pegs such that some of its portion lies vertical and remain like a catenary. Show that the least length of the string to be in equilibrium is 2AE, where 2A is the span or distance between the two horizontal pegs. Now the solution is, since the string hangs freely over the smooth pegs, let 2L be the length of the strings, 2S the length of the portion hanging between the pegs above the directrix, then 2L is equals to 2S plus 2Y, or L is equals to S plus Y, which is equals to C cos H x by C plus C sin H x by C, which is equals to C e to the power x by C, which is equals to C e to the power A by C, as 2x is equals to 2a. So differentiating this equation with respect to C, we get dl by dc is equals to e to the power a by c minus c into a by c square into e to the power a by c, which is equals to e to the power a by c into 1 minus a by c. Now differentiating again, we will get d2l by dc square is equals to e to the power a by c into 0 plus a upon c square plus 1 minus a by c into e to the power a by c into minus a by c square. The length L is least when dl by dc equals to 0, that is c is equals to a. Now d2L by dc square is positive for this value of c, and the least length of string is equals to 2L is equals to 2 into c e to the power a by c, which is equals to 2a e to the power a by a, which is equal to 2ae. So the least length is 2ae. Now the another topic is application of theory of equilibrium on the system of forces, that is points on central axis. Now this topic also I will be explaining out through an example. So the question is, a force F acts along the axis of Z and a force MF along a straight line intersecting the axis of X at a distance c from the origin and parallel to the YZ plane. Show that as this line turns round the axis of X, the central axis of the system generates the surface m square z square plus m square minus 1 into y square whole into c minus x whole square, which is equals to x square z square. Now the solution is, the force F acts at 0, 0, 0 along z axis whose direction cosines are 0, 0, 1. The force MF acting at c, 0, 0 along the line CL parallel to YZ plane, that is perpendicular to x axis. If CL making an angle theta with y axis, then its inclination to z axis and x axis are, hence direction cosines of straight line CL are 0, cos theta and sin theta. Thus F acts along the line x upon 0 is equals to y upon 0 is equals to z upon 1, and MF acts along the line x minus c upon 0, which is equals to y upon cos theta, which is equals to z upon sin theta. The components of forces parallel to the axis are 0, 0, f and 0, mf cos theta, mf sin theta, or capital X1, capital Y1, capital Z1, and capital X2, capital Y2, and capital Z2. Now x we will calculate through summation of x1, which is equals to 0, y is equals to summation of capital Y1, which is equals to mf cos theta, and capital Z is equals to summation of Z1, which is equals to 1 plus m sin theta f. Now we will be calculating L1 M1 N1 and L2 M2 and N2. So we will calculate as I L1 is plus J M1 plus K N1, and after solving we will get L1 as 0, M1 as 0 and N1 also as 0. Now similarly we will be calculating L2 M2 and N2. So after solving this we will be getting L2 as 0, M2 which is equals to minus MCF sin theta, and N2 we will get as MCF cos theta. Now capital L is the summation of capital L1, which is equals to L1 plus L2, which is equals to 0, and capital M and capital N we will be calculating out in the similar manner, as capital M is the summation of M1, which is equals to minus MCF sin theta, and capital N is the summation of capital N1, which is equals to MCF cos theta. Now the equation of central axis are L minus small y capital Z minus small z capital Y whole upon x equals to M minus small z into capital X minus small x into capital Z whole upon capital Y, which is then equals to n minus small x into capital Y minus small y into capital X whole upon capital Z. Now putting the values of respective terms, we will get the equation as minus y into 1 plus m sin theta plus mz cos theta whole upon 0, which is equals to minus mc sin theta plus 1 plus m sin theta whole into x whole upon m cos theta, which is then equals to mc cos theta minus mx cos theta whole upon 1 plus m sin theta. Now this is the one complete equation, and in this we will take out the first two, and after solving we will get it as m cos theta into minus y into 1 plus m sin theta plus mz cos theta equals to 0. So after solving this we will get minus y into 1 plus m sin theta plus mz cos theta equals 0. So on solving this we will be getting y upon z equals to m cos theta upon 1 plus m sin theta and minus my sin theta plus mz cos theta equal y. This is equation 1, or we can write it as minus y sin theta plus z cos theta is equals to y upon m. And in the previous equation we will take out the last two terms and we will calculate it as minus mc sin theta plus 1 plus m sin theta x whole upon m cos theta is equals to m cos theta into c minus x whole upon 1 plus m sin theta is equals to c minus x y upon cz. This was the equation, and we will be taking out the last two, and we will get as mz sin theta x into x minus c plus zx is equals to y into c minus x m cos theta. Now dividing by m into c minus x, we get y cos theta plus z sin theta is equals to zx upon m into c minus x. This we will take as equation 3. So to find the surface generated by the central axis, we have to eliminate theta from equation 2 and 3. Now squaring and adding equation 2 and 3, we get y square plus z square is equals to y square upon m square plus z square x square whole upon m square into c minus x the whole square. This implies y square plus z square into m square into c minus x whole square is equals to y square into c minus x whole square plus z square into x square. So this implies c minus x whole square is into y square into m square minus 1 plus m square z square is equals to z square into x square, and this is the final equation which we had to solve. Now the another topic is application of theory of equilibrium on virtual work. So this topic also I'll be explaining out through an example. So this is the question: a uniform beam of length 2a rests in equilibrium against a smooth vertical wall and upon a smooth peg distant b from the wall. Show that by principle of virtual work that the position of equilibrium, the rod is inclined to the wall at an angle theta is equals to sine inverse b by a to the power 1 by 3. Now here's the diagram. Now the solution is given angle MBL is equals to theta and AB is equals to 2A. So AG is equals to GB, as we can see in the figure, is equals to A. So ML is equals to small b. W acts at G and is fixed at line ML, that is at peg M. So we have to take the distance GK from for the work done. Then the kg is equals to GD minus KD, which is as BL is equals to KD, as we can see in the figure. Now in triangle MLB, B upon small b upon capital BL is equals to tan theta. Therefore BL is equals to B cot theta, small b cot theta. So this implies BL is equals to KD, as I have told previously, which is equals to b cot theta. Now GD is equals to a cos theta, therefore kg is equals to a cos theta minus b cot theta. So giving a slight displacement such that theta changes to theta plus delta theta, equation of virtual work done is equals to minus capital W delta kg is equals to 0, as W cannot be equal to 0. So this implies delta kg is equals to 0 and delta a cos theta minus b cos theta cot theta equals 0. So this implies a sin theta plus b cosec square theta equals to 0, as delta theta cannot be equal to 0. So this implies a sin cube theta equal b. So this implies theta is equals to sine inverse of b by a 1 by to the power 1 by 3. So here comes to an end. I hope you all like the video and thank you for watching.